Hello. In today's video we're going to be looking at Chapter 16, Lecture 14, Learning Objectives 3 and 4. We're going to be looking at Kb using Ka, and then we're going to be looking at a salt solution and determining if it is acidic, basic, or neutral based on the cation and anion within the salt. Okay, so base equilibrium is just like acid equilibrium, but we use the base dissociation constant instead of the acid dissociation constant. So we call this Kb. So our Kb is our base dissociation constant. And that's what we use instead of Ka. However, when we're doing our dissociation, we're going to have an X in here, and this is going to equal our hydroxide concentration, not hydronium concentration, because we are in base. Okay, so our dissociations can look one of two ways. It can be some base that we're going to denote as B, reacting with water to produce the conjugate acid and hydroxide. So it's a base because it produces hydroxide. Or we could have our conjugate base from a weak acid reacting with water to produce our initial weak acid and hydroxide. So it just depends on if we just have a regular base, so like an ammonia base, or if we have the conjugate of a weak acid, which is again a base. So if we have a acid and a weak base, or a base and its weak acid conjugate, we can relate those. So take for instance NH4+. This is an acid. When it reacts with water, it produces hydronium and ammonia. We know this is an acid because it has additional hydrogen and it has a positive charge, and as such it has a Ka associated with it. Its conjugate, ammonia, when it reacts with water, ammonia is a base, so it's going to produce hydroxide, and its conjugate, ammonium, sorry. And that has a Kb associated with it. If we combine these two equations and then we combine our K's for this, we see that we cancel out our ammonia, cancel out our ammonium, and what we get left with is two water molecules dissociate to produce hydronium and hydroxide. So our Ka times by our Kb is equal to Kw. Okay? And we could look at this a different way. We could actually just take our Ka value, multiply it by our Kb value, which we take our Ka, hydronium, times by ammonia, divided by ammonium, times by our Kb, hydroxide, ammonium, ammonia, and again we cancel out these, giving us hydronium and hydroxide, which is equal to our Kw. So if we have a acid and its conjugate base, or a base and its conjugate acid, we can multiply Ka and Kb together for those to get Kw. So Ka times by Kb equals Kw for any conjugate acid base pair Obviously, we have to have a Ka and Kb, so we're talking about weak acid, weak base. Okay. Also, if we were to take and manipulate this a little bit, we'd find that our pKa, remembering that our pKa equals negative log Ka, and our pKb equals negative log Kb. We can put this information in here, and actually we would get pKa plus pKb is equal to pKw, which is equal to 14. Okay. So let's try this out. We want to take the pKa of HF at 3.36 and determine what our Kb for our fluoride ion is. So HF is an acid, and then F minus is its conjugate base. So we know that Ka times by Kb would give us Kw in this case, or pKa plus pKb is equal to 14. Either one will work. So I'm actually going to start here where my pKa is 3.36, and I'm going to solve for my pKb, and I get a pKb equal to 10.64. Then I'm going to take 10 to the negative pKb is equal to Kb. So my Kb would be equal to 10 to the negative 10.64, giving me a value of 2.3 times 10 to the negative 11. Okay, let's look at our acid-base neutralization reactions to bring into the idea of the acid-base properties of salts. So, just as a reminder what an acid-base neutralization reaction is, it's a reaction between an acid and a base that produces an ionic compound. Or produces a salt. And a lot of times water too. Okay. A lot of them are considered double replacement reactions. But not all of them. Okay, and then what happens is if we add in our acid and our base together in correct proportions, so stoichiometrically they're equivalent. So, might have to do a reaction for that. We consider this to be no longer corrosive. That's because we have neutralized both our acid and our base. Okay, so generally at this point we have a pH of 7, but that's only if the acid and the base are strong. So that's our neutral point. Okay. wanted to real quick take a side note and talk about our types of neutralization reactions. There we go. Sorry. So we have 3 types, and they're based on the base. So we have hydroxide-based neutralizations, here we have a hydroxide base, right? So the net ionic equation for a hydroxide base is OH minus plus H plus goes to H2O, and everything else is considered spectators. So for instance, we can have some metal hydroxide plus some random acid, and when they combine, they produce water and a salt. Okay, and that will be the way that every single hydroxide base neutralization reactions work, where we produce a water and a salt. So everything besides our hydroxides from our base, our H plus ions from our acid, becomes our salt. Our next is an amine base. So this can be nitrogen. And let's go specifically, it's going to be, we're going to have some R group with nitrogen. The R group can be hydrogens, it can be carbons, it's just anything attached to a nitrogen with a pair of electrons. So it has to have a pair of electrons. This acts as a Lewis base. And when it reacts, it produces a Lewis adduct. Okay. So we can have something like NH3 reacting with HCl, and we produce the Lewis adduct NH4Cl. So the hydrogen goes to the ammonia species, and then it becomes a salt, so the anion from the acid attaches and makes one Lewis adduct. Okay, our last type is carbonate or bicarbonate. Base. So with our carbonate base, we have CO3 2 minus plus 2H plus goes to CO2 plus H2O. Okay. And again, it doesn't really matter what we have on there. We can have some sodium ions on there, whatever we would like. I guess I can't write down there. So, moving on to an example. So we can have Na2CO3 plus 2 HCl's go to carbon dioxide plus Na2CO3 plus 2 HCl gives you carbon dioxide plus water plus a salt. If we have a bicarbonate base, we have HCO3 minus plus H plus goes to H2O plus CO2, and again everything else is just a salt. So NaHCO3 plus HCl goes to H2O plus CO2 plus NaCl. So there are different types of bases determine what type of reaction we have. So hydroxide will produce water plus a salt. Amine produces a Lewis adduct. And bicarbonate is going to produce CO2 water and a salt. So our Lewis adduct, by the way, is a salt. So all of them will produce a salt. Hydroxide and carbonate will produce water as well, and then carbonate will produce CO2. Okay. Now, let's look at the salt. So each one of these is going to produce a salt. And we want to know about the properties of that salt. So our salts themselves, the cation is going to come from our base. Our anion is going to come from our acid. So anion is from acid. Cation is from base. Okay. Now, if the acid it came from is a strong acid, then it is the conjugate of a strong acid, which means it is pH neutral. However, if it is from a weak acid, the conjugate of a weak acid is a weak base. Okay, so it will be a neutral anion if it's from a strong acid, a basic anion if it is from a weak acid. From our cations, these come from our bases. If it is the conjugate of a strong base, it will be pH neutral. And then here we're talking about group 1 and group 2 metals, right? And then if it is a conjugate of a weak base, it's going to be a weak acid. And the last thing we look at is if it's a highly charged cation, then it will be acidic. Okay, so putting these together, when we put our cation and our anion together, we can determine if we have a neutral salt, acidic salt, or basic salt. So if we have a neutral cation, so this came from a strong base, and we have a neutral anion, because it is from a strong acid. Together they will form a neutral salt. An example of this would be sodium chloride. The sodium came from sodium hydroxide, the chlorine came from hydrochloric acid. Together they produce a neutral salt. We can have a neutral cation, so from a strong base. A conjugate base of a weak acid. So a basic anion. And if we can combine a neutral cation with a basic anion, we produce a basic salt. An example of this would be sodium fluoride. Sodium came from sodium hydroxide, a strong base. Fluorine or F- came from HF, a weak acid. The conjugate of a weak acid is a weak base, so sodium fluoride would be a basic salt. Next we have a acidic cation. And it's acidic because it is the conjugate acid of a weak base. And then we can have a neutral anion, so it's from a strong acid. And when they combine, they produce an acidic salt. So an example of this would be NH4Cl. NH4 comes from NH3, a weak base, and then Cl comes from HF, a strong acid. If we have an acidic cation, a basic anion, so an acidic cation from a weak base, a basic anion from a weak acid, the acidity or basicity will depend on Ka and Kb values. Okay, an example of this would be aluminum sulfate. That would be an example of a species that it comes from a weak base, aluminum hydroxide, weak acid, HSO4 minus, so we would produce a salt that could be basic or acidic. So, just to kind of wrap it up, we can have a cation and anion, they're both neutral, so the salt is neutral. And this comes from a strong acid plus strong base neutralization. Okay. If we have an acidic cation, and the anion is neutral, then the salt will be acidic. Okay, and this comes from a weak base plus strong acid neutralization. If we have a neutral cation, basic anion, we'll have a basic salt. This comes from the neutralization reaction of a strong base plus weak acid. And then lastly, if it's an acidic cation, a basic anion depends on Ka and Kb. So whichever is larger, Ka or Kb, that will determine which it is, acidic or basic. As in, if we have a Ka that's larger, it will be acidic. If we have a Kb that's larger, it would be basic. Okay, so let's check out how we're doing with this. So we have calcium bromide. Calcium came from our our base, so it's calcium hydroxide. And then bromine came from our acid, HBr. Calcium hydroxide is a strong base. HBr is a strong acid, so it would be a neutral cation plus neutral anion. So we have a neutral salt. NaF. Na comes from sodium hydroxide. F comes from HF. Sodium hydroxide is strong. HF is weak, so we have a neutral cation. A basic anion. So we have a basic salt. Okay, next. Fe comes from iron hydroxide. Cl comes from HCl. Iron hydroxide is a weak base. HCl is a strong acid, so we have an acidic cation. Neutral anion. So we have an acidic salt. Last one, NH4. Cl came from NH3. CO3 came from H2CO3. So these are both weak. So we have an acidic cation, basic anion. So it would really just depend on Ka and Kb. Okay, so let's check that. Let's check that real quick and see how it goes. So we have NH42CO3. So if we look at our our cation and our anion, we can see that each of them have the ability to hydrolyze water. Producing producing hydronium and hydroxide. So our Ka for NH4 plus is equal to 5.6 times 10 to the negative 10. Our Kb for CO3 2 minus is 1.8 times 10 to the negative 4. We see that this is stronger. So it's going to basically produce more hydroxide than the ammonia can produce hydronium. So we would say that this is a basic salt. Okay. That's everything for this lecture video. I will see you guys later.